A nation without borders is not a nation. The United States of America gets back its borders.
When Donald Trump entered the White House, it caught the world off guard. And from all the debates that followed, one project rose above everything else, a border wall stretching nearly 3,200 kilometers across the American frontier, steel rising almost 30 feet high, set deep into reinforced concrete, a barrier designed to look permanent, immovable, almost unbreakable. But why build something this massive? And how do you even construct it in terrain this hostile? Let's take a closer look. The answer begins decades before Trump, with a border that functioned like a door left slightly open. For years, the southern boundary saw constant attempts at illegal entry. In 2019, U.S. Customs and Border Protection recorded more than 851,000 crossing attempts. For comparison, that's more than the population of San Francisco in 1 year trying to cross a single line. Pressure increased, so the first fences appeared. The 1990s. President Bill Clinton authorized initial barriers. Later, George W. Bush expanded them. Obama continued, but those structures were short. A few meters high, easy to climb, easy to cut, a temporary speed bump across a continent. The political pressure behind the project wasn't just security, it was cost. Every attempted crossing triggers manpower, processing, transportation, detention, and healthcare expenses. The government calculated that even small reductions in crossing frequency could save hundreds of millions annually. But a weak barrier offered no long-term leverage. Every hole patched led to another one opening somewhere else. By 2016, Trump turned the project into a central campaign message. Build something far stronger, far taller, and far harder to breach. The first idea was a solid concrete wall, a single massive slab, but Homeland Security rejected it. Agents needed visibility. A solid wall would block line of sight. So the design shifted. Tall steel posts, known as bollards, strong, high, see-through. This became the template for the wall we see today. Bollards brought another advantage, modularity. Concrete is monolithic. One crack spreads. Steel posts can be replaced one by one. A damaged section doesn't compromise the entire structure. Maintenance teams could remove, repair, and reinstall individual units without shutting down long stretches of the border. Then came the hardest step, surveying the land. The planned route runs almost 1,930 miles across the U.S.-Mexico border. Every terrain type imaginable sits along that line. Soft desert sand that sinks under heavy weight. Wet clay near the Rio Grande. Hard, rocky mountains across Arizona and California, terrain as tough as natural concrete. Engineers measured elevation, drilled soil samples, mapped stability, calculated foundation depth for every zone. This survey stage determined everything that followed. Surveying also exposed another challenge: remoteness. Many border regions are hours away from paved roads. Transporting machinery required temporary access paths, sometimes graded over uneven desert. Fuel trucks followed construction teams constantly, not a small detail in 40°C heat where engines overheat and hydraulic systems strain. Next came the foundation, the part nobody sees but the entire structure relies on. To support steel posts nearly 30 feet tall, the first step was digging. A long, continuous trench, 24 to 32 inches wide, 6 to 10 feet deep. It sounds simple. It wasn't. This became one of the most time-consuming phases. Soft desert? Excavators work smoothly, but most of the border isn't soft. It's rock, granite, sedimentary layers, material that refuses to move. Regular machines were useless, so crews brought hydraulic rock breakers connected to heavy excavators. These machines hammered the ground non-stop, fracturing stone into removable chunks. After the rough trench was formed, a specialized machine took over, the trencher. These units often run 250 to 400 horsepower diesel engines, enough power to cut deeply and cleanly through stubborn earth. Excavators carved the first pass. Trenchers refined it, straightening walls, leveling the bottom, crushing residual rock. A conveyor constantly carried loose material away to keep the trench clean. Because trenchers cut continuously, they can process hundreds of meters per day, a massive boost for a project this long. On difficult terrain, trench teams rotated in constant shifts. Night operations used powerful floodlights and thermal imaging to detect wildlife before excavation. Anything that wandered into the work zone, from cattle to wildcats, could shut down digging instantly. Delays cost money. Precision cost even more. With the trench ready, workers installed the steel reinforcement cage. Vertical bars, horizontal ties, a long steel skeleton running the full length of the trench. Then crews poured a reinforced concrete layer, 10 to 20 centimeters thick. This created a flat, stable base strong enough to hold the massive steel panels without sinking or shifting. When the concrete bonded with the rebar, it formed a continuous foundation block. Strong against wind, strong against twisting, strong against the desert itself. This part of the process mirrors techniques used in highway overpasses. The difference? Overpasses need to handle vertical loads. Here, the pressure was lateral. Wind, impact, soil movement, all pushing sideways. So the foundation had to act like a buried beam, stretching for miles. With the foundation set, the project reached its visual transformation, assembling the steel walls. The bollards, the main elements, arrived next. Each one is a hollow steel tube, square or round, roughly 26 feet tall, about 10 millimeters thick. The hollow core is intentional, lighter to transport, easier to lift, and ready for concrete filling if additional strength is needed. Each post weighs 250 to 400 kilograms. Heavy-duty trucks moved them from factories to the site. Posts were stacked in layers secured with steel straps and delivered in bulk. Once on site, cranes lifted bundles into temporary storage. Impact had to be avoided. Bending even a few millimeters would complicate later alignment. Every delivery required coordination with Border Patrol agents. Construction crews often worked meters away from active crossing attempts. Security escorts accompanied trucks in high-risk regions to prevent theft or tampering with materials. Even a damaged panel could halt progress for days. Next to the work zone, crews built a fabrication area. Here, they welded posts together into full panels, typically 4 to 6 posts per panel, depending on width. Working in sections speeds everything up. Instead of lifting individual posts dozens of times per hour, cranes move large panels directly into place. But accuracy became critical. A few millimeters of error at the welds could tilt a full panel and compromise the entire alignment. Welders often worked in extreme conditions. Temperatures exceeded 40 degrees Celsius. Steel absorbs heat rapidly, forcing teams to rotate every few minutes to prevent burns. Windstorms sometimes shut down welding completely. Sparks travel far in dry brush. Once welded, panels were ready for installation. This step, setting, aligning, and locking them, formed the backbone of the entire wall. Cranes lifted each panel, sometimes swaying like massive sails in desert wind. Panels weigh hundreds of kilograms. They stand almost 30 feet tall. A sudden gust could destabilize everything. So workers held guide ropes, coordinating with crane operators to position each panel precisely over the trench. Once lowered, the most critical part began: alignment. Using laser levels, spirit levels, tension lines, and experience, engineers positioned each panel perfectly vertical. Even a small tilt would create gaps, weaken the structure, or ruin the long straight line of the wall. Maintaining a perfectly straight line over uneven terrain is harder than it sounds. The earth isn't flat. Hills, dips, and natural curves force micro-adjustments. If engineers miscalculated even slightly, the visual alignment would break, noticeable from kilometers away. After alignment, workers temporarily welded the base to steel anchors or pre-placed frames. These welds held the panel steady until concrete locked it permanently. Then the concrete trucks moved in. Fresh concrete was poured around the base. It filled every gap between steel and soil. Workers used vibrating tools to eliminate air pockets, ensuring strong adhesion. When the concrete hardened, it acted like a hidden anchor. It locked the panel deep into the earth, resisting pulling, vibration, and attempts to pry the structure loose. In some zones, near roads or weak soils, crews added a wider concrete pad extending about 5 feet outward from the wall. This did 3 things: spread the load more evenly, reduce erosion and sinking after rain, make digging under the wall extremely difficult. Instead of soil, any attempt would hit thick concrete first, a major deterrent. This outer pad also helped maintenance teams. Vehicles could drive closer without destabilizing the soil. Inspection robots, tested in limited areas, rolled across the surface to scan welds and check structural integrity. With the structure fixed, workers cleaned the entire surface using high-pressure water hoses. This removed dirt, sand, mud, oil, welding slag, and metal fragments. If residue remained, Paint wouldn't bond properly, so workers sprayed from top to bottom, panel by panel. This cleaning step improved durability and corrosion resistance, crucial in harsh desert climates. Paint wasn't only cosmetic, it reduced thermal fatigue. Dark steel heats rapidly. A consistent protective coating ensures expansion happens evenly across the structure. Irregular heating leads to long-term stress cracks. Then came the final protective layer, razor wire. Civilian crews don't install this. Military units or border patrol teams handle it due to the security risks. Razor wire is engineered to cut on contact. Coils are lifted by specialized tools or installed by hand. Metal brackets and hooks secure them tightly to prevent shifting. With the wire installed, climbing becomes almost impossible. Some sectors also installed motion sensors and vibration detectors, not part of the wall structure, but integrated into the overall security line. These systems trigger alerts when the razor wire is disturbed. Years passed. Hundreds of miles of new fencing were completed, crossing points narrowed, Border Patrol gained more control. The cost, according to U.S. Customs and Border Protection, exceeded $15 billion. Materials, transport, surveillance, labor, and maintenance continues to add hundreds of millions annually. Even so, cartels still find ways around the wall, and environmental concerns remain, especially along the desert ecosystem and Rio Grande region. Experts warn about wildlife movement disruption and altered water flow. The wall brought benefits, but it isn't perfect, and the challenges along the border continue. Then the narrative shifts from construction mode to long-term impact. Because a wall this large doesn't just change the border, it reshapes everything around it. For decades, the southern states have absorbed the hidden costs of an unstructured boundary. Local economies, emergency services, hospitals, and law enforcement all carried the weight. After the wall's expansion, patterns along the border began to shift. Traffic funneled into fewer, more controllable points. Large stretches that once required constant patrols became lower-risk zones. Agents could redeploy to strategic areas instead of spreading thin across hundreds of miles. Economic models showed something interesting. Every stabilized crossing zone reduces pressure on detention centers, local hospitals, and county resources. In regions where the new sections stand, operational costs fell. Fewer transports, fewer high-speed pursuits, fewer helicopter hours, fewer emergency deployments. The wall also altered infrastructure planning. Some counties repurposed former high-incident corridors into industrial zones, storage yards, or energy installations. Areas once avoided by investment gained long-term utility because they no longer sat exposed to unpredictable movement. Construction towns saw temporary boosts too. Equipment yards, rebar suppliers, concrete plants, and trucking fleets expanded to support multi-year border work. For some small towns, this created the closest thing to an economic boom they'd seen in years. Hotels filled with welders, crane operators, and survey crews, the invisible workforce behind the steel. Once sections opened, logistical behavior changed. Smugglers who relied on open desert routes had to move farther into hostile terrain, increasing failure rates and reducing throughput. Border Patrol noted sharper detection zones. Sensors perform better when movement concentrated into narrow crossing funnels instead of sprawling across wide-open desert. Over time, entire industries adapted. Drone surveillance companies tested prototype systems along the wall's spine. Road repair teams upgraded access routes originally built for construction machinery. Fiber optic lines were laid to support new monitoring towers, improving connectivity in remote regions. Real estate shifted too. Parcels near the border, once considered high risk, saw gradual price stabilization. Some ranchers reported fewer cut fences, fewer nighttime trespasses, and fewer disrupted livestock operations. This created more predictable insurance profiles and reduced long-term property losses. There were environmental trade-offs. Water flow and wildlife migration changed in some pockets, forcing biologists and engineers to negotiate new mitigation plans. Protected species corridors required rerouting or specialized openings, balancing security with ecological stability. But operationally, the wall introduced something the border rarely had before: consistency, predictable movement, predictable patrol patterns, predictable risks. Maintenance carries a price. Steel weathers, concrete cracks, wind loads stress the posts year after year. But even with ongoing costs, frontier communities report more stable conditions than the decades prior. A wall cannot eliminate every crossing. It cannot solve every structural issue along the boundary, but it reshapes the terrain of the problem. redistributing pressure, redirecting flows, and buying time. Exactly what an engineered barrier is designed to do. 2,000 miles, hundreds of towns, dozens of agencies, and one structure that now defines the modern American border. A reminder that infrastructure doesn't just build barriers, it builds the framework for how a region functions.